Welcome to this lecture on the Simplex method. Today, we are going to explore one of the most powerful mathematical algorithms ever created. It is a tool that helps industries around the world maximize their profits and minimize their costs by finding the absolute best solutions to complex problems. By the end of this session, you will understand exactly how this clever search strategy works. Now that we know what we are aiming for, let us understand how the simplex method actually works. Imagine you are blindfolded on a mountain made of flat, tilted triangular faces. You cannot walk up the middle, you can only walk along the edges. You start at the bottom, feel for the steepest upward edge, and walk to the next corner. You repeat this until all edges go downwards, meaning you have reached the peak. The simplex method does exactly this mathematically. It evaluates the corners of a geometric shape called a feasible region, always moving to a neighboring corner that improves the profit until it finds the absolute best answer. This visual perfectly illustrates the mountain climbing analogy we just discussed. Look at the shaded area on the graph. This is our feasible region, representing all valid solutions that obey our rules. The simplex method does not wander randomly through the middle of this shaded area. Instead, it starts at the origin, where profit is zero. It identifies the edge that increases profit the fastest, shown by the red arrows, and travels to the next corner point at 4,0. From there, it checks again and moves to the highest profit point at 3,1.5. It stops here because any other move would decrease the profit. Before we can apply this edge-walking algorithm, we have to prepare our mathematical model. The simplex method cannot work with inequalities. It requires strict equations to maintain a perfect balance. We achieve this by introducing something called a slack variable to each constraint. Think of a slack variable as an imaginary container for your unused resources, like leftover factory hours or extra materials. If you have a maximum limit of 18 hours, your actual usage plus the unused slack time must exactly equal 18. This simple trick allows us to use standard algebra to solve complex optimization problems. Let us see how this conversion looks mathematically. The formula on screen shows a standard equation where a slack variable has been added. Conceptually, this comes from an inequality where 3 times x1 plus 2 times x2 was less than or equal to 18. Here, x1 and x2 are the units of products we are making. The symbol S1 is our slack variable, representing the exact number of hours that go unused. If we produce nothing, x1 and x2 are 0, meaning S1 becomes 18. As we increase production, the slack variable decreases, ensuring the total always balances perfectly to 18. Now that we have our formula structure, let us solve a concrete example. Imagine a small workshop making two products. We are given an objective to maximize our profit, Z, which equals 3x1 plus 2x2. We are limited by two constraints. Resource 1 limits x1 to 4 and resource 2 limits x2 to 5. We chose the simplex approach to find the exact number of each product to make. Our first step is to move all variables in the objective function to the left side, so it equals 0. Then we add slack variables S1 and S2 to our constraints to turn them into strict equations. Continuing with our setup, we look at our rearranged objective function. The -3 is the most negative coefficient, meaning producing x1 gives us the biggest immediate jump in profit, so x1 becomes our entering variable. We rearrange our first constraint to solve for x1, giving us 4 minus s1. The reasoning here is to see how x1 behaves relative to the slack. We then substitute this expression back into our objective function. By expanding and simplifying, we mathematically update our profit equation to reflect that we are now producing 4 units of the first product, bringing our current profit to 12. Looking at our updated objective, we still have a -2 attached to x2. This tells us that increasing x2 will further increase our profit. So we are not done yet. We take our second constraint and solve for x2, getting 5 minus s2. We substitute this into our objective function to simulate moving to the next corner of our feasible region. After expanding one last time, all coefficients on the left side are positive. This means any further changes would decrease profit. Our final answer shows a maximum profit of 22, achieved by making 4 units of the first product and 5 of the second. That first example was simple. But what happens when resources are shared between products as they are in real factories? For this, we use the tableau method. This method organizes all our equations into a structured grid, making it easier to handle complex calculations. Instead of simple substitutions, it uses a formal ratio test to figure out which resource will run out first, identifying the leaving variable. Then, it uses systematic row operations to pivot and transform the entire set of equations at once. Let us look at the mathematical formulas that drive these row operations. Here we see the core formula for a pivot operation in the tableau method. Conceptually, this comes from the need to isolate our entering variable so it has a coefficient of exactly 1, just like solving simultaneous equations. The symbol R1 new represents our updated equation, while R1 old is the original constraint equation. The number 6 here represents our pivot element, which is the specific number intersecting our entering and leaving variables. By dividing the entire row by this pivot element, we scale the equation down. If the pivot element increases, the resulting coefficients in our new row become smaller, reflecting a tighter constraint on the remaining variables. Let us apply this to a factory scenario. We are given an objective to maximize profit Z equal to 5x1 plus 4x2. This is subject to a machining constraint and an assembly constraint, which we have already converted to standard form using slack variables S1 and S2. We chose the tableau approach because both products share the machining and assembly hours. Looking at our standard objective function, the most negative coefficient is -5. Therefore, x1 is our entering variable, meaning we want to produce as much of product 1 as possible to quickly boost our profit. Continuing our factory problem, we need to know which resource runs out first. We do this by performing a ratio test. For the machining department, we divide the 24 available hours by the 6 hours required per unit, giving a ratio of 4. For the assembly department, we divide 6 available hours by 1 hour required, giving a ratio of 6. We must choose the smallest ratio because the machining department will run out of time before assembly does. This makes S1 our leaving variable, and the number 6 becomes our pivot element for the next step. Now we apply our pivot formula. We divide the entire first equation by our pivot element, 6. This isolates x1, giving it a coefficient of exactly 1, resulting in our new row 1 equation. Next, we must eliminate x1 from the second constraint to keep our system balanced. We do this by subtracting our new row 1 from the old row 2. This row operation ensures that x1 is completely removed from the second resources equation, updating our assembly constraint to reflect the resources used by our new production plan. Finally, we must update our objective function to see our new profit. We do this by adding 5 times our new first equation to the old objective function. This specific multiplier is chosen to perfectly cancel out the negative 5x1 term. Our final answer for this iteration shows a new objective equation with a profit of 20. Notice there is still a negative 2/3 coefficient for x2. This means the process is not finished. And in a full solution, we would repeat these steps choosing x2 as the new entering variable until all coefficients are positive. Now that we have seen the math, why does this matter? The Simplex method is one of the most important algorithms in modern history. It forms the backbone of industrial optimization worldwide. Every single day, major airlines use this exact mathematical process to schedule their crews, ensuring flights are staffed without violating labor constraints. Delivery companies use it to route thousands of trucks, minimizing fuel costs. Factories rely on it to plan production schedules that maximize output. Without this method, companies would have to rely on trial and error, wasting millions of dollars and countless hours. Let us review our key takeaways. First, the Simplex method transforms complex multivariable decision-making into a reliable mechanical algebraic process. Second, we learned that by introducing slack variables, we can convert limiting inequalities into strict equations, allowing us to use standard algebra. Finally, the algorithm works by efficiently navigating the corners of a feasible region, always moving in the direction of greatest improvement and stopping exactly when the absolute best outcome is found. You have now covered the full mechanics of the Simplex method, giving you the power to optimize resources in almost any real-world scenario.